Hi everyone, welcome back to my channel. Today we are going to discuss about system of resistors. So let's begin. Electrical circuits are basically closed in continuous paths through which electrical current can flow through. Here I'll just mention briefly that these lines that I've drawn are actually wires. This is the key. This element that is present in the circuit is actually the ammeter. And then lastly, this is the battery. This is the positive end and this is the negative end, and conventionally we say the direction of current is in a circuit is from the positive end to the negative end. There is a whole story behind why we have chosen to give this the direction when the actual direction is the opposite direction, but you can find that out for yourself. This can be a little fun activity that you can do on your own. Well, these are not the only elements that are there in the circuit, because circuits are much more complex in real life. I'll just add this one more element here. Now this, my friends, is a resistor. What is a resistor? Well, it's in the name basically. Resistors have to do something with resisting. Resistors resist or oppose the flow of current itself. Well, that doesn't make a whole lot of sense. Why would we place something deliberately in a circuit which is opposing the current or which is stopping the current from flowing? Well, we place these kind of elements to gain more control over the circuit. It's like adding a system inside the circuit which lets us have more control over the amount of current that is entering the circuit and modulating it according to our needs. So that is the purpose of a resistor inside a circuit. And you may have heard of this word called as rheostat. Rheostat is a device which can provide resistance inside a circuit. So you can connect a rheostat to your circuit. I'll show you a picture here of a rheostat, and you can see that it is a device which can be connected to a circuit, and you can move its knob to and fro to increase or decrease the amount of resistance that you want to give into the circuit. Since you can change the amount, or there can be a variation in the amount of resistance through this rheostat, it is also known as variable resistance. So now I come to Ohm's law. And what it gives us is a relationship between the current, which is I, and the voltage or the potential difference. So it gives a relationship between these two elements, and voltage we represent by a V. So what it says is that the voltage in a circuit is directly proportional to the current in the circuit. As in, when we increase the voltage in a circuit, the current or the amount of current also increases proportionally. And when we remove the sign of proportionality, the full equation is V is equal to IR, and this is how we actually get our resistance, my friends. So this R here is nothing but resistance. Let's talk a little bit about resistance. I'm going to write it in red so that you know that resistance is related to opposition. So there are two things that we might be interested in. And the first one of those two things is that resistance actually is directly proportional to the length of the conductor. If this is my wire 1 with length L1 and it's 5 centimeters long, and this is my wire 2 with length L2 and this is 9 centimeters. So L2 will have more resistance than L1. The longer the length of the conductor or the wire, the more the resistance will be. Now if you think for a second why that is, you would have to go to the reason of why resistance actually occurs. That resistance is the result of the electrons that are moving, which are causing the current bump into the atoms of the material through which it is moving. So for example, there are electrons that are moving inside our wire here. So let me just zoom this diagram in. Inside the wire, of course, there are the atoms of the wire itself, because everything is made out of atoms. So obviously this material of wire is also made out of atom. And we also know that electricity is basically electrons moving. So whenever electrons get in motion, we say that electricity is flowing. So here our electrons are moving in this direction, and they are going to clash with the atoms of the material through which they are flowing. So this clashing of electrons with these atoms, they cause resistance. Imagine if these atoms weren't present in some places, the flow of electrons would have been that much smoother. So this is the reason why resistance occurs. Now if we were to understand where length comes into play, we can imagine that if this wire in which the electrons were moving was much shorter, then the amount of bumping into the atoms would be lesser, and by comparison, if there was a longer wire, there would be more incidences of the same bumping. Of course, the crash of electrons into the atoms would occur more in the second instance because there is more length. So therefore, resistance increases when we increase the length of the conductor. Let's move on to the next point. Resistance is inversely proportional to the area of cross section of the conductor. Resistance will decrease with increase in area of conductor and will increase with decrease in area of conductor. So let's unpack this also. Let us look at this scenario. Now in the first instance, I've drawn a wire with a thick cross section and this is a thinner cross section. So in which of these do you think flow of electrons will be much smoother and easier? In which lane do you find yourself driving more easily when the lane is wider? There is lesser resistance to your driving. So of course, here the electrons are going to find themselves flowing much easily, while in a congested road they're going to find more resistance. This is A1 and this is A2. So in A1 and A2, which will have more resistance? Of course, A2 is going to have more resistance because it has a thinner cross section, the area is less. That means it is that much more congested for the electrons to flow. That means more resistance. In a circuit, we can find sometimes that more than one resistor is present and it can be arranged in more than one ways. So let us see both the ways. Okay, so we have two examples in front of us. The first one is called a series arrangement. Why do we call it series? Because as in series, the episode goes from 1, 2, 3 and it is aligned one after the other. In a similar fashion, the resistors are aligned one after the other. When the current flows from here, it's going to enter the first resistor, exit the first resistor, then enter the second resistor, exit the second resistor, then enter the third resistor, exit the third resistor, and then come back here. The same current is going to flow through all three resistors. So in series, I remains same while voltage differs. So this is a good way you can learn this trick, that in series I is same. So if I remain same, that the other component will change, that is the voltage will differ. While here you can see resistors are arranged very differently. So this kind of arrangement is called parallel arrangement. And what happens in parallel arrangement is the resistors actually face each other. So here when the current will exit the battery and enter one of these points, it is actually going to divide in two different directions. So I'm going to represent this by a red color. So here the current is going to divide and then it's going to enter two different directions. So this is one of the key features of parallel type of arrangement of resistors, that the current is not same, it divides. While you can see that I have actually connected a voltmeter here, so voltage on parallel connection is same. So since one is not same, the other one will be same. So V here is same. Then after exiting the two circuits, the current is going to add and then it's going to come out and enter the battery again. So now that we have covered this and understood what parallel and series type of arrangement is, we can actually go to our derivation of how do we get our formulas for calculating resistance in a system of resistors. We knew of two things. One was that in series resistance, I remains same and voltage changes. So in series type of circuits, we know that the current through all three resistors will remain same, whereas the voltage will change. So the voltage on the three will be the sum of individual voltages across the resistors. So V series will be V1 plus V2 plus V3, that is the voltages across each of the resistors. Well, we are aware of this sweet little formula, V is equal to IR. This is the Ohm's law. So we can say that this is 1 and this is 2 using 2 IR, and then I can write series, and I'm not writing anything against I because I is the constant here. So I is common, IR1, then IR2, then V3 can also be expressed as IR, so it's going to be IR3. Then I can be taken common. When we take I common, it's going to be R1, R2, R3, and here it's going to be IRS. And we can cancel these i's, and then we're going to be left with our formula on how to calculate the resistance for all the resistors that are connected in series. So I can say that this is R1, this is R2, and this is R3. This is my key and this is my battery, positive, negative, and I can mark my current directions. So in parallel, I have two kinds of information. One is voltage is same while current is different. So I'm trying to find the current here, and I will say that I is equal to I in all three resistors. So the individual I across all three resistors, and the sum of it is going to give me the total current that is flowing in the circuit, right? So I'm going to say IP. V is equal to IR, and it also gives me I is equal to V by R. So here I can substitute, if I say that this is 1 and this is 2, in 1 I can substitute this 2 and say that IP can also be expressed in the form of V by R. So I can say V upon RP. V, I'm not saying VP because V is going to be same across all three resistors. So it's going to be V upon R1 plus V upon I2 can be expressed as R2, and then V by R3. Then the same way in which we did the series, I'm going to take V common. That will give me R1 plus 1 by R2 plus 1 by R3, and then we can cut out the V, and then that gives me the final formula, which is 1 by Rp, that is parallel is 1 by R1 plus 1 by R2 plus 1 by R3. And this is the formula that is going to help me with my calculations of resistors in a system. Here R1 is 2 ohm, R2 is 3 ohm, and R3 is 6 ohm. And we have to calculate the total resistance of this system. Now I think we all will be able to identify if the system of resistors is in series or is in parallel. So here I can clearly see that it is in series. So I'm just going to apply my formula here, which was Rs is equal to R1 plus R2 plus R3, which will give me 2 plus 3 plus 6, that is 12 ohm. So if I forgot to tell you earlier, ohm is the SI unit of resistance. Let's do another one. So here we know that these three resistances are connected in parallel, because you can see that the current, when it is leaving the battery, it is going in different directions. In R1 itself, the current is taking two turns. Half of it is going into R2 and half of it is going into R1, and then again when the current is going into R2, half of it is going into R3. So this type of connection in which the current bifurcates or it is going in different directions is a parallel arrangement. Here also we are going to calculate the total resistance of the circuit, and since it is connection in parallel, we are going to use that formula of parallel connection. So according to this formula, it's going to be 1 by 40 plus 1 by 40 plus 1 by 20. Then you take the LCM, which is going to be 40, so it's going to be 1 plus 1 plus 2, that is 4 by 40, 1 by 10, and then if 1 by Rp is 1 by 10, then by that mathematics, resistance in parallel is going to be 10 ohms. Another question that arises, what if I want to calculate the total current? We have already discussed that in a parallel arrangement of resistors, the total current will be the sum of the individual currents at each resistor. So you will have to calculate the I at each resistor. So say the voltage for the entire circuit is 12 volts. You will be calculating the current at each resistor. So for example, for the first resistor, you can use the formula V is equal to IR and then V by R. And then by that formula, we have the V, which is going to be same in parallel. And then the resistance R1 is 40, so that is going to give us current of about 0.3, and then we're going to write A because ampere is the SI unit of current. This is I1. So similarly you can also calculate an I3. So if I2 comes out to be 0.3 as well, because it is the same value, 40 ohms, and then for 20 ohms it's going to be about 0.6 ampere. Then for the total current, you can just add all of these values and it's going to give you, and that is how you will calculate total current in the circuit. Let's do one where both kind of resistors are present together. Here we have to also calculate the total resistance of this circuit. Now this may seem complex to you, which one is in parallel with which, but let me just tell you a very simple way of trying to analyze which resistor is in parallel and which is in series. The method is that you're going to trace the path of current. I'm going to say that the current is flowing in this direction, right, from positive to negative. So it enters R1, then from R1 I can see that the current is flowing in R2 as well as R4. R1, R2 and R4, the current is bifurcating. Then when the current is going inside R2, it is going into R3, and then the current is again going into R5 and then coming back into our battery. One thing is clear to me from this diagram, that we have to firstly identify resistors which are in series with each other, so we can easily calculate their resistance first. First of all, those resistors will have the same current flowing in them. There will be one direction in which the current is flowing, and I can already see one of them, that is R5 and R1. So current from R5 is coming here and straight away it is entering R1, right? There is only one direction, so I can say that R1 and R5 are in series, and I know that the resistors which are in series, I can straight away just add them for their resistance. So R1 and R5, their resistance is going to be 3 ohm plus 3 ohm, it is 6 ohm. Then rest 3, R4, R2 and R3, I can see that there is some kind of bifurcation of current. Let's unload these three first. In R2 and R3, I can see that the current that is going inside R2 is entering R3 without any bifurcation. That means that R2 and R3 are also in series. So I'm going to calculate simply their resistance also. That's going to give me 6 ohm. Both in front of R2 and R3, R4 is placed, so it is in parallel with both of them, because when the current is entering from R1 into R2, the current is bifurcating into R4, and when the current is exiting from R3, current from R4 is also entering that stream. So I can say confidently that R4 is actually in parallel with both of these resistors. Since the combined resistance of both of these resistors we have already calculated, that is 6 ohms, I'm just going to simply calculate the parallel resistance of these three, which is going to be 1 by R4 plus 1 by 6. So that will give me 1 by 3 plus 1 by 6, that is 2 by 6, 3 by 6, that is 1 by 2. So Rp is 2 ohm. So now for this system of resistors, the resistance has come out to be 2 ohm. For the total resistance, I just need to add the resistance of these two with this system. So that is going to give me the total resistance. So for this system, R1 and R5 we have already calculated. So I'm just, for total resistance, I'm going to add 6 ohm plus 2 ohm from the parallel arrangement. That is going to give me 8 ohm in total. So I hope you enjoyed this video, guys. An update for all of you, there is going to be another video that I'm going to put out that is going to contain just the questions with some songs in the background, so that you can enjoy solving these kind of questions and practice them for your exams. So I hope you will check that out too. And if you like this video, show your love through some comment or like, or in the comment section you can also advise me on the type of videos I should do, what kind of content you want to see from my side. Thank you very much. Till next time.